For years, NASA's Gateway Lunar Space Station existed only as plans, simulations, and ground-based equipment awaiting assembly. This changed with the first successful operation of the Power and Propulsion Element, the station's core. This was not a symbolic test. It was the moment Gateway transitioned from a concept to a functioning spacecraft. The system, which will generate 60 kilowatts of electricity, maintain the station's orbit around the Moon, and provide communication with Earth, is now active and operational. Long confined to engineering laboratories and design reviews, Gateway has crossed a threshold. It is no longer just equipment on the ground. It is the foundation of humanity's first permanent outpost beyond Earth's orbit, and it has just been activated. Let's now examine together what has been activated, why it changes everything, and how it enables humanity's continuous presence in deep space. The Power and Propulsion Element, PPE, is no ordinary module. It is Gateway's central nervous system. All other components, living quarters, laboratories, docking ports, communication systems are entirely dependent on the PPE's ability to generate power and control the station's position in lunar orbit. Without the PPE, Gateway cannot function. The final activation confirmed that this critical system is functioning exactly as designed. Engineers at Lanteris Space Systems in Palo Alto, California, working under the supervision of NASA's Glenn Research Center, successfully powered up the spacecraft's main electrical systems. Power began flowing through the circuits. Subsystems responded. Computers booted up and confirmed operational status. The Gateway's power backbone proved for the first time that it can support an entire lunar outpost. The PPE is designed to continuously generate 60 kilowatts of electrical power. To put that into perspective, the International Space Station generates about 120 kilowatts of power, but it operates in low Earth orbit with solar panels constantly facing the Sun and regular resupply missions. The Gateway will orbit the Moon in deep space far beyond Earth's magnetosphere and will be exposed to higher radiation and more extreme temperature fluctuations. It must operate reliably for extended periods with minimal support. The 60 kilowatts provided by the PPE is sufficient to power life support systems, high-bandwidth communication systems, navigation equipment, scientific instruments, and visiting spacecraft simultaneously. This power level provides the station with flexibility for expansion over time, adding modules and capabilities as missions require. Power generation comes from massive roll-up solar panels, each about the size of a football field end zone. These are not rigid panels like those on most satellites. They are flexible, lightweight sheets that unfold like yoga mats once deployed in space. This technology, called ROSA, has been tested and proven effective on the International Space Station. In lunar orbit, these panels will track the Sun and convert solar energy into electricity using state-of-the-art solar cells, providing uninterrupted power throughout the Gateway's 15-year design life. However, power alone is not enough. The Gateway will occupy one of the most challenging orbits ever attempted, a nearly linear halo orbit around the Moon. This orbit is ideal for lunar missions because it provides access to the entire surface of the Moon while allowing constant communication with Earth. However, it is inherently unstable. The gravitational effects of the Moon, Earth, and Sun constantly push the station off course. Without active correction, the Gateway would drift off position within a few days. This is where the PPE's propulsion system becomes critical. Unlike traditional spacecraft that use short bursts of chemical rockets, the PPE uses a solar-powered electric propulsion system. Electricity generated by solar panels powers 7 advanced electric thrusters. 3 of these are 12-kilowatt advanced electric propulsion system thrusters manufactured by L3 Harris. These are the most powerful electric thrusters ever flown in space. 4 6-kilowatt Hall effect thrusters manufactured by Busek provide redundancy and fine-tuning control. These thrusters collectively ionize xenon gas and eject charged particles at extremely high speeds to generate thrust. This process is far more fuel-efficient than chemical propulsion, using only 1/10 of the propellant while providing steady, continuous thrust for precise orbital control. This approach fundamentally changes how space stations operate. The International Space Station relies on periodic reboosts from visiting spacecraft to maintain its orbit. Gateway will autonomously control its position and make constant small adjustments to stay where mission planners need it to be. Engineers can reposition the station to optimize communication with Earth, support specific lunar landing sites, or prepare for incoming spacecraft. This level of control transforms the Gateway from a passive object into an actively managed platform capable of supporting complex multitask operations. The successful power-up operation also confirms that PPE construction is proceeding as planned. The spacecraft's main electrical systems are covered with protective outer panels. The solar panels are complete and undergoing final testing. 7 electric propulsion engines are being installed and integrated into the power system. Xenon propellant tanks and liquid fuel tanks for chemical backup thrusters have been installed. All major subsystems are complete. or nearing completion, bringing Gateway closer to its next critical milestone: integration with the Habitation and Logistics Outpost, HALO. HALO is the module where astronauts will live and work. It provides pressurized living quarters, docking ports for visiting spacecraft, and the internal systems necessary for human habitation. When PPE and HALO are combined at NASA's Kennedy Space Center in Florida, they will form the core of the Gateway. The Gateway is a complete, self-sustaining space station capable of supporting crewed missions. The integrated spacecraft will then be loaded onto a SpaceX Falcon Heavy rocket and launched toward the Moon. It will travel in deep space for about a year before entering its final orbit. From a scientific perspective, Gateway represents something unprecedented. Unlike the International Space Station, which orbits safely within Earth's protective magnetosphere, Gateway will operate in true deep space conditions. Radiation levels will be significantly higher. Extreme temperatures will be more severe. Resupply missions will be infrequent. Every system must be designed for long-term autonomous operation with minimal maintenance. PPE enables this by providing reliable power and precise orbital control, allowing the station to serve as a stable platform for research that cannot be conducted anywhere else. The Gateway will also serve as a crucial testbed for technologies needed for future Mars missions. For example, solar-powered electric propulsion is expected to play a significant role in transporting cargo and equipment across interplanetary distances. By operating the PPE in lunar orbit for years, NASA and its partners will gain invaluable experience with this technology under real deep space conditions. Similarly, the life support systems, radiation shielding, navigation methods, and autonomous operations tested on the Gateway will provide direct information for the design of spacecraft and living quarters for Mars exploration. The commissioning of the PPE also signals a change in the organization of space exploration. The Gateway is not solely a NASA project. It also includes contributions from the Canadian Space Agency, the European Space Agency, and the Japan Aerospace Exploration Agency. Over time, additional modules and laboratories will be added, each drawing power from the PPE to increase the station's capacity. Commercial companies have also joined the project to develop logistics systems, experiments, and services that will use Gateway as a base. The PPE's ability to provide abundant and reliable power enables this international and commercial expansion, transforming Gateway from a single mission into a permanent deep space infrastructure project. For the Artemis program, Gateway provides a critical staging point. Astronauts traveling to the Moon will dock at the station, transfer to lunar landers, and descend to the surface. After completing their missions, they will return to Gateway before returning to Earth. This architecture enhances safety, allows for more flexible mission planning, and enables sustainable lunar exploration for years to come. Instead of launching directly from Earth to the lunar surface, crews can use the Gateway as a hub, making missions more efficient and reducing the risk associated with each landing. The powering up of the PPE is a quiet but profound milestone. For the first time, the Gateway is functioning not as a collection of components, but as an actual spacecraft. The electrical systems are operational. Power is flowing. The core is active. What remains are the integration, testing, and launch steps. These steps will transform this operational spacecraft into humanity's first forward outpost beyond Earth's orbit, opening a new chapter in deep space exploration and laying the groundwork for missions to Mars and beyond.